All right. Hi, everybody. I'm Dan Greenwald. Thank you so much for coming. It's great to be here. So let's get started with today's lecture. So I'm going to be talking to you guys about structural models of housing and mortgages. It's probably a bit different from what you've been looking at so far, maybe even a little bit different from the traditional urban approach. I'll be looking at things a little bit more from the finance or macro side, but I think it can be, hopefully you'll agree, kind of a fruitful way to look at things as well. So today we're gonna, like I said, be talking about structural models of housing and mortgages. So usually when I come into a room and start talking about housing and mortgages, I need to do a lot of song and dance to motivate why this is an important topic. In this room, probably not so much, right? But what really got me interested in this field is just how important this is for, as kind of a finance or macro-based person, is kind of how important this is for the typical household balance sheet, right? So, as you may know, the typical household doesn't really have much in terms of directly held stocks or bonds. Their balance sheet is really a huge asset, which is a house, and then a huge liability, which is a mortgage. And if you understand those two things, you basically understand the financial situation of the median household in the US, at least. So in this, for today, we're going to be talking about what determines house prices at equilibrium and what role is played by credit, by mortgage credit, in determining those prices. So the roadmap for today, we'll see how far we get. I'm going to give you guys a basic setup, kind of just a basic model of what might determine house prices and why credit might play a role in determining house prices. That's going to kind of be the workhorse or whatever, the template that we're then going to build on with other applications. Then I'm going to take you through two kind of extensions, two ways we can sort of extend this basic setup. One is in terms of basically thinking more carefully in a deeper way about the fact there are multiple constraints on how much you can borrow at the same time. And then a second one about segmentation between housing markets, in particular between rental and owner-occupied housing. And I'll explain to you why these are kind of, I think, good questions and why they're important. And both of these are going to be kind of centered on, I'll walk you through in detail using kind of one of my own papers as a case study, not because I'm vain, but because I actually know, I don't know, maybe I am, but because I know those inside and out, and I can really tell you how they connect to the basic setup and what's new and what are the main takeaways for modeling. So this area in general is not so much one where maybe like some others, there's like a couple canonical models and I should just teach you those. This is really more thinking carefully about different features of the market and thinking about how you might add those to kind of a very basic framework to generate results. If I have time, I'll also give you guys, because will probably, for most of you, be my main opportunity to talk to you. I think people at this stage in the career often are helped by a little bit of advice. I'll give you a little bit of final thoughts about the research process if we have time. That's kind of a maybe. All right, so one thing you may be wondering, presumably there's a bunch of kind of empirically minded people in the room who might be wondering, what is the point of this stuff? Why bother writing down structural models? Why not just go to the data? Real estate is one area where we often have pretty good data. But I think even so, it's worth doing it. So here's a motivating example from history. So in the 1990s, the GSEs, meaning Fannie Mae and Freddie Mac, switched from manual underwriting to automated underwriting, okay? You can read more about this in this very interesting paper by Johnson and Sur-Ilan. And so what's the big idea behind this? Well, manual underwriting says, you look at these borrowers' characteristics and there's just certain rules you have to satisfy, like your payments income or DTI, it's often called, has to be below some number, right? And they switched from doing this to automated underwriting, where they use these desktop underwriter or loan prospector algorithms. What do those things do under the hood? Basically, they're just running a regression. So they estimate a default regression, and then they basically plug in the right-hand side values to produce a fitted value for the regression. And they say, okay, this is your predicted default probability, and they just see if this thing is above or below some cutoff, okay? So when you run a cross-sectional regression of defaults on characteristics, what you're going to find is one of the key underwriting variables, this ratio of your mortgage payments to your income. In industry, it's always called DTI, debt to income, but it's not your debt, it's your debt service. So if you want to think about it, that I always call it payments income to try to be clear, but if you think of it as debt service, that's fine too. This thing is actually not a good predictor of default. So you can see another of Stephanie's papers for that. And the intuition I always have is like, it's really for default, it's more important whether you lose your job or not than what your income was when employed, right? We kind of know from, Ganong and Noel and other papers that most defaults happen after people experience some kind of liquidity shock, income shock, or some unusual medical cost, or divorce, or some big tail events, right? So your income while you're employed, while everything's going well, is not always that relevant, right? Now, whether that's the true intuition or not, it is true that this regression, it will not come out as a strong predictor. And so when you compute the fitted value, the DTI just doesn't matter that much for your default probability. And so the automated underwriting system is kind of ignoring this variable. But because this was all cross-sectional, it failed to take into account the general equilibrium effects. And in particular, what this means is that the largest underwriters in the country are now relaxing a constraint on tens of millions of borrowers, right? And actually, what hopefully you'll understand by the end of the lecture is this made house prices go up, right? And then later made house prices crash. And so now you have a bunch of defaults because households are underwater. So it's not because of this thing where cross-sectionally, maybe the ones with higher DTI did not default more than the ones with lower DTI, but you miss this huge GE effect that you caused a giant boom and bust in house prices, okay? And so that's why structural models are useful. Often, especially in housing markets, there's a big national component to the cycle or a big regional component to house prices. In order to think about how different credit market interventions would affect these, and these are really important for regular people, we need to understand the GE effects, right? So the models that we're going to cover today are designed to capture these effects, as well as counterfactual policies, like that you would want to have run before doing something like this, right? Okay, good. So that's kind of the motivation. So now let's go into the first part, which I'm going to present a basic just setup of how you might think about house prices in a simple structural model. I will go through, at least just for the very first one, the nuts and bolts of how you solve it. For a bunch of people, it might have been a while since whatever class you took this in, maybe, I don't know, macro 1, if ever. So if this is like kind of review for you, please bear with me, but I want to make sure even kind of more empirically minded people are on the same page. Okay, so we're going to consider the problem of a household who optimizes this Bellman equation, right? So I guess technically I should have the max in here, but the value, you're going to come in with a certain amount of housing and income, and then you're going to try to maximize your utility from today's consumption and housing. Often in these models, by the way, we assume that you have to make some kind of assumption about whether you actually get to consume the house the period you buy it. It doesn't really matter, but in this case, I'm assuming you come in with the house. That's the one you're living in while you're deciding how much housing to buy. And then if you buy a house, a new house, it will start applying next period. And then you have your continuation value from your housing choice today. Oh, and this should be your income tomorrow. Okay, so then you have a budget constraint, which is that your non-durable consumption has to be less than or equal to your income minus whatever you spend on your net housing purchases, right? So your new housing, whatever you choose for your new house size HT, and for now, we're going to assume you just buy a new house every period. That's the simplest assumption. We can revisit that later. That costs you P times H, where P is the price of housing. Let's say this is like per square foot. This is the number of square feet. But then you came in with a house, maybe net of depreciation delta. Okay, so your net purchase is what you're buying net of what you came in with and can sell, basically. So if we want to solve this constrained optimization problem, we just set up the Lagrangian, right? Where we're going to have this stuff, but then we're also going to include this constraint. I've rearranged it so it just has to be greater than or equal to 0 times some multiplier lambda, okay? And if you take the first order conditions, where anything with a subscript letter is going to be the derivative, partial derivative with respect to that argument, you're going to find that, well, it's kind of a trivial problem, but you can maximize this thing with respect to consumption. The first order condition is that it shows up here, positive. So 0 is going to be equal to the derivative of all this stuff, but I'm going to move some terms over when they're the other sign. So here it's going to show up positive, the derivative of this, and here it's going to show up minus multiplied by lambda. So I'm going to move the minus term to the other side. You get this thing. Similarly with the price, or sorry, with the housing decision. So this says that basically the marginal utility consumption is the benefit that you get from relaxing your budget constraint by 1 unit of consumption. And this says that, so as you increase your housing, where is that going to show up? First, you have to pay for it. So it's going to show up in your budget constraint, right? Here, negative. So I'll put this will be the negative side. And then you get some benefit that next period, you're gonna have more housing when you walk into the period, okay? So that's kind of the main idea. All right, so then we need to basically put together this thing, and I won't be so pedantic about doing all the algebra for the future. We're just gonna do it once. So this thing, we can compute using the envelope theorem, right? So the derivative of the value function with respect to this argument is just basically gonna be the derivative of this Lagrangian just one period ahead. So now this is kind of the derivative with respect to like ht minus 1, because next period that it will be the lagged one. So it shows up here as the marginal utility. And then it shows up here as in your budget constraint, okay? So if you look at that, this is what it looks like. So basically, that's what I said. You get some, when you enter the period with more housing, you get the marginal utility of that housing, and you get to keep whatever's left over next period, which has this value in your budget constraint. And then if we kind of pull out this lambda t plus 1, it looks like this. So I'm just going to separate that, pull that out to make it easier for the next step. And then we're going to put it all together. So if I go back here, I take this expression. I'm going to divide through by lambda t. And then I'm going to substitute in later the fact that lambda t is the marginal utility of consumption. We get this thing. So and then basically all I'm going to do here is substitute in the fact that lambda t is just marginal utility of consumption. And now this is maybe going to start to look a bit more familiar, right? Because actually this contains objects that we use, well, at least I use a lot, probably many of you do too, right? So this thing here, beta times the marginal utility of consumption tomorrow divided by the marginal utility of consumption today, that is the stochastic discount factor, right? If you have a consumption-based model, right? And then this thing, the UH over UC, that's the marginal rate of substitution between housing services and non-durable consumption. That actually, I'm going to call that rho. So the SDF will be lambda. This is going to be called rho. Rho is, the reason why I'm using that is because rho is like rho for rent. This is what the rent usually is in one of these models, right? The rental price is usually this marginal rate of substitution, okay? So what you end up with at the end of the day is that the price has a very intuitive financy looking formula. It's equal to the expected value of some stuff in the future discounted by the stochastic discount factor. So whenever you're doing kind of an asset pricing formula, you're always going to be multiplying the future stuff by the SDF. And then what do you get? You get the cash flow. So rho is kind of like the rent, right? It's like the value of the housing services that house is going to give you, which is very intuitively like the imputed rent. Plus, you get to keep the continuation value of whatever housing is left over after depreciation. Okay, so I think it's a fairly intuitive formula. All right, so that's going to be our starting point. And for the rest of the lecture, we're going to be working with formulas that kind of start from here and then add stuff on top of it. Okay, any questions so far? All right, so now the first thing we're going to do is add in mortgage credit, right? You'll notice there was no credit here. You're just doing everything kind of with cash in the budget constraint. So we're now going to add a couple things. So we're going to assume that the household can borrow at some interest rate Rn subject to a loan to value limit. And this is what you'd find in a lot of classic models like Jacobiello model. In this case, the budget constraint looks the same, but has a new term because now you can actually, you don't have to pay for all your housing in cash. You can borrow with the mortgage. And whatever you borrow, that's actually extra resources that you could consume, right? You don't have to use your own consumption to pay for that, right? But of course, whatever you borrow, you have to pay back. So then you have to pay back last period's mortgage at whatever gross interest rate you promised. This is, let's assume, one period debt for now. You can, of course, make this long-term debt. And then one thing that's actually good to keep in mind, even though it's a little bit pedantic, is that mortgages are usually nominal, right? You promise to pay back in dollars. Whereas these models, usually we keep track of things in real terms. Consumption is just like the amount of stuff you're consuming. So you usually actually want to deflate what you're paying back by the inflation between yesterday and today, which is what this term is doing. Now, how much do you want to borrow? Well, potentially a lot, right? But you can't always do that. So what I'm also going to add in is a loan to value limit that says that your mortgage amount is less than or equal to some fraction of the value of the housing you're purchasing today, where theta is going to be the maximum loan to value ratio. Okay. So this is kind of a real world constraint. It's true. If you really go buy a house, you have to abide by this. All right. So what does this do to the house price? Well, now our Lagrangian is going to have a new term in it, which is going to be, ooh, there's a mistake in here. Sorry. We're going to have the LTV limit. This is the budget constraint. The budget constraint should also have this new term in it. So sorry about that. I'll update this and post it after I'm done. So the budget constraint will be updated, and you're going to have this new term that's like a second constraint inside the Lagrangian. One tip, you might notice that I put this thing inside with the lambda t. This is actually really helpful because it makes everything measured in consumption units rather than utils. So if that makes sense to you, great. If not, don't worry about it. Just know it's often actually simplifies the problem in a, doesn't add any meaning to it. It's just a scaling that actually turns out to be quite convenient. So what do the optimality conditions look like now? Well, now we have the housing one that's going to look basically pretty similar to before, except that now you're going to have this term here, which is coming from the LTV constraint. And what is it saying? It's basically saying that you realize, you take into account that when you buy more housing, it actually relaxes that limit because more housing means you can borrow more. Then you also have this separate mortgage condition, which says that basically, well, here's the main effects of getting the mortgage. You get $1 today, which you value at lambda. And you also get the derivative with respect to, of your value function with respect to walking into the next period with more mortgage. Okay. So if you rearrange using kind of the envelope condition, what you're going to find is this thing. And I'm not going to walk through the exact math again, but this thing should look quite familiar. This is basically the condition that we saw before with a new term in red in the denominator. Okay, 1 minus mu t theta. And then we're going to have a new optimality condition with respect to m, which is basically going to pin down what this multiplier mu is. And I'll talk about that more in a second, where this is going to basically take into account the fact that, in the Lagrangian, you realize that as you borrow, you get these potential benefits, there's some costs, but also you're tightening your constraint, right? Okay, good. We're now, by the way, I'm writing lambda b because this is now the borrower's SDF. Any model where you have credit, someone's got to be lending, right? So now we have to start being a little bit careful about distinguishing between the borrower and the lender. All right, so this is the main thing that I want you to focus on that we added so far, right? We took our house price equation. The numerator is identical, but now we're dividing it by something. And this denominator is going to be smaller than 1, right? Because mu is a multiplier. It's got to be, it could be 0, but it's got to be at least 0. It's non-negative. And theta is going to be a number like 80%, 0.8. So, if you multiply these terms together, it's a positive number. So subtracting positive number makes the denominator less than 1. So that's actually pushing prices up, right? And what does this term reflect? It reflects that when you can borrow and you have an LTV limit, housing now takes on a collateral value at the margin, right? So what is this term saying? Well, remember, theta is the extra amount you can borrow for every $1 of housing you purchase. That's what an LTV limit says. If you buy $1 of housing, you can borrow 80 cents. Mu is the shadow value of an extra $1 of credit. So it's how much do you value, kind of in consumption units, $1 of mortgage, right? Including the fact you have to pay it back. But at equilibrium, people borrow because that's not an NPV 0 transaction. They actually get some positive NPV, some positive value out of borrowing, even when you consider that they have to pay it back. And we'll see why just in a second. So the marginal collateral benefit, this mu theta, is the product of the two. It's saying for every $1 of house I purchase, I can get theta of credit. And then I'm thinking to myself, how much do I value that credit? That's at value mu. So this kind of maps from $1 of housing purchased into the actual value you receive at the margin from the credit you got collateralized by that purchase. Okay. In general, this thing is going to push up house prices. And if you have a credit relaxation, like you increase theta, you can see that's going to make this term smaller sorry, it's going to make this term bigger, the denominator smaller, and P bigger. So in general, relaxing theta, all else equal, is going to push up prices. So credit, you already get that looser credit standards can increase house prices, which is what a lot of papers, using this kind of framework, like the original Yacoviello paper, exploit. Okay, any questions so far? All right. So let's talk now quickly about mu, because this thing I think doesn't get a lot of attention, but what is it? So mu is equal to 1 minus the mortgage rate times the expected, I'll call this thing the nominal stochastic discount factor. It's like the value of $1 for sure tomorrow, taking into account the fact that dollar may have inflation. There may be inflation between today and tomorrow. Okay. And so if you're familiar with kind of asset pricing, in an unconstrained world, this thing is usually the nominal risk-free rate times this thing for the marginal investor is usually just 1. That's one of these classic finance 1 equals E of MR formulas, right? But here it's not. And the reason is that this is not the marginal pricer of a risk-free bond. This investor actually would not be interested in investing in a risk-free bond. In fact, the rate is low enough that they don't want to be investing. They strictly want to be borrowing, so much so they've gone up to their borrowing limit. Okay. And so basically this mu is a wedge in their asset pricing condition. So we can actually express that a little bit differently, right? So let's call RB the nominal rate which the borrower would willingly save. Okay, so this, if you ask a borrower, not the rate they're getting on their mortgage. Clearly, they don't want to save in that because they're actively going out and borrowing at that rate. But if you ask the borrower, at what rate would you kind of be indifferent between borrowing and lending? Let's call that RB, and that should satisfy this kind of asset pricing condition. Well, then it turns out that mu you can write like this. It's basically the difference between the rate at which they would voluntarily save and the mortgage rate sort of scaled by RB. The scaling is not important. The important thing is up here, right? It's basically that it reflects the difference in the kind of reservation rate at which the borrower would hypothetically save and the rate that they're receiving on the mortgage. So the more that the borrower thinks that the mortgage is like a good deal, the rate is lower than the rate that they would hypothetically save at, the bigger this number will be. Okay, so it's really reflecting like how good of a deal they feel like they're getting on the mortgage. And that makes sense, right? Because they have to repay it. So the only way that, at equilibrium, you have a shadow value of borrowing is if you feel like the dollar that you get is better than the repayment you're going to pay back. And so the more that you think the repayment schedule is like a good deal for you, the higher this mu will be. And of course, if these are equal, mu will be 0. Then you're unconstrained. You'd be happy to not borrow at all, or even save at that rate, so the constraint is not binding for you. In steady state, usually if you have this kind of SDF and you have a steady state where consumption is constant, then the SDF, stochastic discount factor, hopefully that's clear. Where did I put it? Is just beta, because these terms are the same. So if you substitute that in for these, and then you do some rearranging, you can also reflect it as the difference in the betas here, meaning the discount factors between the saver and the borrower, right? So this mu in steady state is also reflecting the difference in patience between these two groups. Is another way to think about it. So if the borrowers are just as patient as the saver, mu is 0. But as the borrowers become more impatient compared to the saver, this mu grows. And by the way, of all the parameters in these models, I think the one that gets the least attention is beta B, or more accurately, this difference, right? This because credit only matters to the extent that mu is positive. And it also is, you can see, for example, this term, when you change theta, the degree to which that matters depends on exactly how big mu is. If you double mu, the effect is double. This difference is critical, and I actually don't see a ton of attention being paid to it. It's often kind of treated as a throwaway. People use standard values. So I don't think it's a great idea. I'll come back to how I like to calibrate this thing a little bit later. Okay, good. Any questions here? Yeah.
In these models, you're either a borrower or the saver, but like in the real world, people are borrowing and saving at the same time, typically, or many households are. How does that map into?
Yeah, so if you wanted to do this, if you think about it, like the rate that you get on saving is never going to be as good as the rate you're paying on your mortgage, right? So you need to add something about you value liquidity. So in this kind of model, you could do it with a hack where you could put some, liquidity in the money in the utility, bonds in the utility or something. In a heterogeneous agents model, you just need risk, right? You need some kind of risk where you're going to arrive, you can't transact in your mortgage period by period, right? This one period thing is not realistic, and there will naturally come out that you may have some precautionary saving. Although there is, this research, I don't know if people are familiar with this kind of wealthy hand-to-mouth style model that's become popular, kind of Kaplan and Violante, where there are a lot of households who, yes, maybe they have like $2,000 in checking or something, but they kind of are not that far from being a zero liquid asset household. So yeah, that's kind of my 2 cents. Other questions here? All right. And one thing about, I guess this kind of gets into another thing about this kind of class of models I'll show you. They're simple, right? They're simple. You have there's 2 types, maybe 3 types, something like this. They mask a lot of heterogeneity, but they make it very clear what's going on, and they're very tractable. So this is kind of a trade-off you're going to be making a lot if you go into structural modeling. Do you want something that's tractable and where you understand exactly what the economics is and the mechanism is? Or do you want to start incorporating more realistic types of heterogeneity? You can, of course, incorporate all kinds of more realistic heterogeneity and heterogeneous agent models, but it often comes at kind of a loss of tractability, a loss of interpretability, and potentially a loss of like the ability to even run certain experiments because the models become so computationally intensive. So I think there's room for both, but the application depends a lot on which one's better depends a lot on the application. And so I do think there's still, even with all the progress we've made with computation, there's still a big role for models you can write down and actually understand what all the equations are doing. Okay, good. So unless there's other questions, if so, feel free to chime in. Let's talk about the first kind of way we can extend this basic framework, which relates to credit constraints, right? So in some sense, what I'm going to show you builds in some sense on this paper. I'm saying in some sense because actually it was funny at the time. We kind of came up with the idea at the same time, but I like the way that they put it in this paper, which is very nice. So, this is kind of a very interesting look at what happens when you start layering different constraints on top of each other. And something very surprising happens. So, basically we saw that in a simple model with only LTV limits, if you increase theta, you're going to increase the price. So now let's consider an extension with 2 constraints and no heterogeneity, okay? So what we're going to do is incorporate, the LTV constraint I showed you before, pH is just P. And then I'm going to add a second constraint that says a borrower just can't borrow more than some limit, M bar. Right now, it doesn't really matter what it is. It just doesn't depend on the amount of housing you buy. Okay, and then we can next I'll fill in what I think this thing should be. So here's kind of, if you do go back and do this optimality condition, the Lagrangian's now going to have 2 constraints in it, okay? One, so if you go back here, we added this constraint for the LTV. Now we're going to have a second one. So I'm going to call the multiplier on the first constraint mu1, and the second one's going to be mu2, all right? My son is a big Pokemon fan. I think he'd be excited to hear me say this. Then what you're going to find is that, remember, this thing came from the optimality condition for housing, right? But housing is only going to hit one of these, just the top one, because this one doesn't depend on housing. So we're going to see the same thing, but it's just going to be the mu1 that shows up, all right? But when you borrow, potentially the multipliers for both of these things show up, right? Because you tighten both constraints when you borrow, but you only loosen one constraint when you buy housing. Okay, so that's what it looks like. Now the sum of the 2 mu's is going to be the same as the one I showed you before. So the total, if you call the total thing just mu, that's going to be exactly the same object. But now it's going to be split into 2 pieces, and only one of the 2 pieces will show up in the house price equation. So this is a surprising result. It's actually been, I think, rediscovered independently like 3 or 4 times. And every person I've talked to who like independently discovered this said at first they didn't believe it, including myself. But there's this weird result that there's this region of state space with positive measure where both constraints bind. Okay, so usually you think you have 2 constraints. So you're kind of in the region where one of them is binding. And then there's a knife edge where they both bind, maybe they're tied. And then you move into the region where the other one's binding. But it turns out that because of the particular way these are set up, and in particular, the fact that the house price enters this constraint, there's this middle region of positive measure. It's not a knife edge, where the constraints kind of drag each other along so that they're both binding at the same time, which is kind of bizarre, but is true. So you can do proof by contradiction, right? So how can you show this? So imagine that only the collateral constraint binds, right? So remember with these constraints and multipliers that if a constraint is binding, then the multiplier is positive. If not, it's 0, right? So if the collateral constraint only is binding, so this is the only binding constraint, then mu1, then mu2 has to be 0 because that one is not binding. So mu1 is just the entire mu, okay? And so then we're back to the formula that I had for you before. If only the other constraint binds, this one, the m bar, then mu1 is 0 because it's slack. That's what we're assuming. And then the price is just this thing without the mu term in it, because this thing is mu1, right? That's the first equation I gave you, basically. So let's call this one Q upper bar, which is when you get the full mu. And let's call this one Q lower bar, which is when you get none of the mu in that expression, right? And so obviously Q lower bar is strictly smaller than Q upper bar, right? It's not, as long as this term is positive, going from here to here is like a substantial decrease. So then it turns out that if M bar happens to be in the right spot between these things, you have to have both constraints binding at the same time, right? Because what's the contradiction here? So imagine that you assume that only the collateral constraint binds, right? Well, if only the collateral constraint binds, that means this one has to be tighter than this one. So this term has to be smaller than M bar. But if only the collateral constraint binds, the price of housing is Q upper bar. And if we plug in, by assumption, if we plug in Q upper bar, that's bigger than M bar, not smaller. So that case doesn't work. That's impossible. But let's assume the other thing. Only this one binds, then the price is Q lower bar. But notice in this case, the alternative constraint is binding. So M bar has to be lower than this thing. And then, but if we plug in Q lower bar, we know that's not true. So actually, both of these cases are impossible in this region. So the only way you can square this thing is if mu1 is actually not 0 and it's not the entire mu. It has to be in between. But how can you do that? The only way that mu1 can be in between mu and 0 is if mu2 is also in between 0 and mu, which means both constraints have to be binding at the same time. And effectively what's happening is you have this region of the state space where in order for the market to clear, oh, sorry, I just did something. These two things have to be equal. And that has to be, importantly, that has to be equal, not just at one knife edge case, but for a region. And what that means is that if you start in this region, and then you start changing some of these things, and you don't change M bar, the other ones are going to have to change to offset it. So what does that mean? Basically, if you, sorry, this thing is going a bit crazy. Right, so in this region, the two things have to be equal, right? And that means that if we sort of set these things equal, sorry, I switched from P to Q for some reason. If you set these things equal, and then you solve for the price, then that price has to be M bar over theta H. So in this region of the state space, if you increase M bar, you increase the price 1 for 1. So whatever this limit is, if you increase it 1%, you increase the price 1%. But in this region, it's falling with respect to theta. If you increase theta by 1%, the price falls by 1%. So normally, remember, this is flipped from a standard model. Usually you have the relaxing credit conditions makes house prices go up. Here you have it make them go down in this particular region, okay? So the intuition, I think, is a bit tricky. I think it will make more sense when I show you kind of my implementation of this. But for now, just keep in mind that when you layer on multiple constraints at once, and one of them is an LTV limit, a lot of wacky things can happen, okay? And in particular, you can find that relaxing the LTV limit can make prices fall. All right, so then this is a very nice paper. They try to explain a lot of things at once. So what they basically are doing is, if you look at the housing boom, what you see is that prices are going up, but then interest rates are going down. So they make this claim that the second constraint needs to be on the lender side, not the borrower side. So in some sense, this constraint should be for a lender, not for a borrower. So why does it matter? It's a little bit subtle, and I don't think it's necessarily clear from the paper. But the reason why it matters is that we assume, what's implicitly being assumed behind the scenes in these models with constraints, is that the constrained party has all the bargaining power, right? You have an unconstrained group. Let's say usually we would think of the unconstrained group as the lenders. The lenders are competitive. But the borrowers can say, gee, I'd love to borrow more, but I can't because of my constraint. So then the lenders will trip over each other trying to get these sort of borrowers, this limited demand from the borrowers by offering them low rates, basically. So in this world where we assume that the borrowers are constrained, although really what it means is that the borrowers are the ones with the bargaining power, the rate at equilibrium is basically going to be this, which is the reservation rate at which the borrowers are willing to borrow. They are limited amounts. Or sorry, this is the lowest rate that the lenders are willing to offer, right? You can see it as a minus mu here. So as constraints loosen, remember mu is like the shadow, it's a multiplier on your constraint. So as you make constraints looser and looser, that thing will go to zero. Eventually, if the constraints are so loose they don't exist, mu will be zero, right? So in this world, rates tend to be rising as you relax credit constraints. And that's counterfactual because during the 2000s housing boom, rates were falling. So what they say is, let's assume it's not the borrowers who are constrained, but the lenders. So in this case, it's actually the lenders who are getting the rate. The borrowers are sort of tripping over themselves to say, look, I'll pay you more, just give me the credit because you guys are the ones rationing. And in that case, the more constrained the borrowers are, the higher the more constrained the lenders are, the higher the rates. Because mu is now entering positively, and that thing, as it goes to zero, will cause rates to fall. So I'm not sure if this is clear from the math, but it should be pretty clear graphically. So let me see if I can draw a picture, maybe here. Not guillotine my water. Okay, so basically what's going on is you have, this is like the amount borrowed, right, which I'll call M. And this is the rate R, right? And so as usual, there's like a downward sloping relationship where at lower rates, you're willing to borrow more. This would be from the borrower's perspective. This has nothing to do with constraints yet. This is just about hypothetical demand and supply. And this is from the lender's side. Of course, the higher the rate, the more willing you are to lend, right? So this is supply, okay? And now what happens in these models is there's like a constraint, okay? So this is like the amount you actually can borrow at equilibrium. It could be an LTV constraint, could be something else. But in general, there's some constraint on one of the parties that's going to limit the amount of borrowing. You can see here that this is actually making the rate at which you transact at this price kind of unclear, right? Because now this is the rate at which the lenders are willing to lend this amount. And this is the rate that the borrowers are willing to pay to borrow this amount, right? So because the market's not clearing, we have this mismatch between the reservation prices, okay? And so in principle, models have to take a stand on, in principle, the market could clear at any price between here, at any rate. And our models usually are implicitly, it's just something to be aware of, they're implicitly taking a stand on what's going on. So the standard model where the borrowers have all the bargaining power assume that the rate starts here, okay? And as you're relaxing the constraint, you're moving up this curve. And so the interest rate's going up, right? So that's why we get these counterfactual predictions that when you loosen credit, the interest rate goes up, which is now what we saw in the 2000s. Alternatively, if you assume that it's that the lenders have all the bargaining power, they're forcing the borrowers to pay the maximum they're willing to pay. We start up here, then actually as you loosen credit, the constraint toward equilibrium, the rate is falling, right? But to be honest, like I don't really think that I guess I have all the text for what I said here. To be honest, I don't think that we really know that either of these are true. I think that the bargaining power question is actually really interesting. It's like an open area for research. It could be that we start here and then we take some path like that. I have no idea, right? I don't think we really know this. My guess is both of these are too extreme. And there's many possible prices. And I don't think it's so much about who's constrained as the fact that there is bargaining power in the mortgage market, and how surplus is allocated is important for what the price ends up being and how that price moves as constraints are relaxed. So I think I haven't seen anyone actually, to my knowledge, do a really good treatment of this issue, and I think it would be an area for possible research. Okay, so now let me get into my implementation of. Okay, great. Of how I actually did this. So remember that in that previous model, the M bar was just like anything, right? It could be any constraint. So what I did in my job market paper is I had to fill in what I thought this constraint was, right? And basically, I did a couple things, but the main thing I'll focus on here is the fact that I posited the second constraint is this what I call payments income, PTI constraint. As I mentioned, if you look in the industry stuff or a lot of research, they'll often call it DTI, but it's not. It's a payments income limit. And then I did a bunch of work to try to make the mortgages more realistic, right? Because if you look at my example, we have these 1-period mortgages where you're buying a new house every period. That's not right, and it actually matters. So I was able to actually model in this tractable setting, like these long-term fixed rate loans that are prepayable. And actually it works pretty well. You'll have to see the paper for that. I'm just going to focus on the house price stuff today. So the main finding is that a loosening of payments income limits appears really important to understanding the 2000s boom and bust, right? I'll argue kind of for some of the theoretical reasons we've already talked about, but I'll be more clear that the amount, changes in LTV limits, which people had been pointing to, actually doesn't really make sense. It doesn't make sense kind of theoretically or quantitatively. Whereas the payments income loosening actually has theory behind it and empirical backing that these things really were loosened, kind of the way I mentioned. So quantitatively, what I find is basically, you can explain about a third of the boom just from the relaxation of this one limit by itself. And actually about half the boom if you include sort of indirect effects through making other shocks amplified, which I'll talk about. Okay, so why is this payments income, what is this payments income limit doing? And why does it change what we think about? Why is it so powerful, right? So here's a simple example, and I think this is actually going to contain a lot of the intuition behind that Justiniano Primatieri Tambolotti result that may not have been intuitive, right? At least the way I explained it. So here's a simple example. Let's consider a home buyer who wants, basically as large a house as possible at the minimum down payment, which I think is a pretty good description of a, new home buyer or many buyers. Let's say this home buyer faces a payments income limit of 28%, which, way back in the 90s, this would be like a comical number today, but way back when was the standard number, before you count other forms of debt. There's a lot of nuance to this thing. And an LTV limit of 80%, which is, was and remains the standard for getting a conforming loan. All right, so let's assume this borrower has an income of $50,000 a year at a 28% payments income limit. Well, that means she can put 28% of this toward her mortgage payment. That means a maximum monthly payment of around $1,200. Okay. So now I need one more thing. We need to assume an interest rate. Let's assume it's a 6% interest rate. In that case, this $1,200 payment is associated with a particular size loan, which in this case is around $160,000. So let's say you take that loan size and you add in the fact you have to make a minimum down payment of 20% on top of the loan. And that would get you to a house price of 200,000, which I've sort of drawn in red here. So if you have bought this house, you put down 80%, that would be 160, which is exactly the amount you can borrow according to your income. So why is this price special? So it's actually special because it induces a kink in the down payment function, right? So basically, this is the amount of down payment you'd have to make on a house with this price. So when the price is low enough, basically, when your payment income limit's not binding, then every dollar that you buy, you can actually borrow 80 cents, and you only have to put down 20 cents of down payment. That's kind of what LTV limit means. And so this thing is aligned with slope 0.2. But once you cross this price, the bank says basically, look, no matter how valuable your house is, we're not going to lend any more to you, okay? Because your income is not high enough to support that. And so from then on, you have to pay basically dollar for dollar in cash. So this thing goes from having slope 0.2 to having slope 1. And this is a very natural place for home buyers to stop and basically target a house with this price, right? So why might that be? Well, imagine you're saving for your down payment, right? And you're just deciding, okay, at what point am I going to stop saving and finally pull the trigger? Here, every dollar that you save is going to get you $5 of house, right? Or if you do a low LTV loan, sorry, low down payment loan like FHA or something like this could be $20 of house, right? But as soon as you cross this line, that goes from being, 5 or maybe more to being $1. So all of a sudden, the effectiveness of your saving goes way down, okay, in terms of improving your purchasing power. And so this is a natural place to stop saving and just buy. So let's assume that a borrower, and people in the data do this, right? It's very robust. Okay, so let's assume a borrower is doing this. They've chosen this kink point, right? But now let's start doing some potential shocks, right? So now let's assume that interest rates fall from 6 to 5%, okay? So in this case, what that's going to do is, so the maximum monthly payment the borrower can make is still the same. It's still $1,200. But now that same $1,200 payment is associated with a bigger loan because the interest rate's lower, right? So to get to the same payment, you have to start with a bigger loan at a lower rate. So if we increase that loan size to the new maximum loan size of $178,000, and we add back in the minimum down payment, this house price at which this kink occurs jumps from 200 to like 223. So you notice it's jumping by like more than 10% in response to a 1 percentage point change in rates, right? Because what's happening is, even though this is a change of 1%, proportionally, this is a change of like, it's 1 percentage point, but it's like 16% on the interest rate. So this thing actually has a very strong elasticity. The interest rates, your interest payment is very sensitive to interest rates proportionally, and therefore so is your payments income limit. So if the borrower follows this kink solution from here to here, this kind of corner solution, she'll actually increase her housing demand by like more than 10%. And if many borrowers do this, you'll see a big increase in prices. So what's going on? I think for intuition, it's like, imagine that this borrower was ready to kind of buy this house, or at the bank, they're doing the final paperwork, and all of a sudden the banker says, hey, look, now you can actually buy, we're willing to give you a bigger loan, right? Given your income, because rates have gone down, you can now get a bigger loan. But there's a catch, which is that the LTV is like a collateral constraint. You also need a valuable enough house to collateralize this loan. So if you want this bigger loan, you actually can't get it with the house you picked out. There's not enough collateral there. So you can get a bigger loan now, but you also have to go out and buy a more valuable house to go with it. And that's why relaxing this limit has a big increase on housing demand, because yes, it gives you access to more credit, but only if you also go out and buy a more valuable property to back it. If these were totally separate limits, if they were unrelated, it wouldn't matter. It's the fact you have both of them in the same model that generates this effect. Okay, so actually you can also think about not just, so reducing the rate is like an endogenous way that you can relax payments income limits, but you can also just relax them. Maybe the lender just decides that they're willing to give you a higher payments income ratio. We'll see this will be important later. This has the exact same effect as a drop in rates, right? It relaxes this limit, it pushes this kink point to the right and increases housing demand. Okay, so that's why relaxing these payments income limits either endogenously by cutting rates or sort of just by changing credit standards can have a big effect on house prices. So now let's do the same for LTV. And maybe the result I showed you before will make a bit more sense. So now I'm going to assume that we relax the LTV ratio, okay, from 80% to 90%. Now in black, I've plotted here the maximum loan size the borrower can get subject to her payment income limit. And now we're not messing with the payment income ratio, the maximum, or with the interest rate. So this thing is going to stay put. But remember, to get this red line, I started from this black line basically, and I added in the minimum down payment of 20%. Well, now that down payment is shrinking because we can make a smaller down payment. So actually the price at which this kink point occurs is actually going down. And if the borrower follows her corner solution from here to here, she actually will demand less housing, okay? And so what's the intuition here? You can do it kind of in like a, household budget way, which is like, well, previously, if the household wanted to downsize from this house to this house, she would have only kept a very small amount of cash, right? Because most of it would have gone toward the fact that she would have had to reduce her loan size as well, because her collateral value would have fallen. But when the down payment is allowed to be lower, she actually can go from here to here and keep the entire difference in cash. So basically, by downsizing, you keep now 5 times as much cash savings, which can be appealing. All right. There's also a way to think about it in terms of the economics of supply and demand, which is really about the supply and demand for collateral, right? So in some sense, it's kind of a loose sense, but heuristically, the size of the loan is the same. So the demand for collateral, the amount of lending we need to collateralize is the same. When the LTV ratio goes up, each dollar of housing is actually able to collateralize more debt. So in some sense, we kind of have the demand for collateral is fixed, but the effective supply of collateral is increasing. And that actually makes the price of collateral, the value of collateral fall, which is a component of the house price. So hopefully it makes a little bit more sense why layering these things can actually make the LTV limit expansion have a negative effect on demand and prices. So that's going to be a feature of the model. Okay, so here's how my model is going to look. And I think maybe there are some lessons here for future modelers. So first, I'm going to have borrowing, right? So by the way, if you do any kind of structural model, it doesn't have to be this kind. I find this kind of slide is so helpful because there are a lot of people who are sort of fundamentally distrusting of structural models, and they want to know why are all these moving parts in here. So if you present them with here's the moving parts and here's why I put them in, this wouldn't work without them, people usually are much more on board. So the first thing I need in this model is borrowing, right? I can't talk about mortgages if there's no borrowing. That means I need some basic heterogeneity. I need someone to borrow and someone to lend. So I'm just going to introduce impatient borrowers who are going to borrow at equilibrium from patient savers, all right? I'm going to make these permanent types with no switching. It's going to be very simple. Preferences are going to be very standard kind of log preferences. By the way, if you see this kind of structure, log plus something times log of housing, that's actually equivalent to log preferences over a Cobb-Douglas aggregate of non-variable consumption housing services, which implies constant expenditure shares, basically. So it's kind of a very standard functional form. Then I don't want this just to be regular debt. I want it to be mortgage debt. So I have to put in housing. I'm going to assume that housing is divisible. I'll come back to this. This is an assumption made in a lot of these simple kind of aggregated models because it kind of saves some headaches. But I'll talk about it in a minute. The assumption that housing is like clay, you can just take a little bit of someone else's house, stick it on yours, can cause issues. I'll come back to this. And then I'm going to have a fixed housing stock. You could add construction, it wouldn't change too much. And then I'm going to fix saver housing demand. So this is where the divisibility is really important. In some papers, like a different Justiniano Primaceri Tambolotti paper, they kind of show that these credit shocks should not necessarily, and like Kiyotaki, Nobu Kiyotaki is a paper about this, they show in certain models that these credit shocks should not have a big effect on prices, because what happens, you change credit around, you change the demand by borrowers, but the savers just come in and offset their demand by buying whatever they're selling or selling whatever they want, right? And this is, if you think about it, these models, for example, predict that like during the housing bust, right, in 2009, 10, whatever, you have these wealthy households who are coming into, downtown Phoenix or downtown some area of Las Vegas, and they're packing up these houses, they're bringing them back over to their kind of Connecticut mansions, and they're sticking them on as like an extra wing of the house, right? That's not really what buying additional property is like. And in reality, there's a lot more frictions, right? It's not that easy, and that's going to make the demand much more inelastic. So one thing to be aware of if you write these models is if you have divisible housing, demand by most of the agents is very elastic. If you give them the opportunity to buy housing, they'll be very happy to do it without sacrificing a lot on the price. In reality, when you think about differentiation in terms of like location, quality level, the fact that having a second home is not like a wing of your first home, people are actually much less willing to absorb housing that other people don't want unless you give them a massive discount, okay? So what I'm gonna do here is I'm gonna make this perfectly inelastic. I'm just gonna fix the saver housing demand to be constant. The saver is not gonna be trading with the borrower at all. I think that's, reality somewhere between, but that's a different paper that has yet to be written. I think if you're gonna make one of these kind of extreme assumptions, I think fixing the saver housing demand to turn off this very counterfactual channel is good. All right, then I'm gonna have realistic mortgages, which are gonna be long-term fixed rate bonds. I have endogenous prepayment in the paper, but you can just imagine that every so many periods you redo your mortgage and then you can transact in the housing market. Then I have some other stuff that really just matters for the kind of more macro application I was doing, so let's skip over it. All right. So now let's go to the credit limit. So the borrowers are going to face two limits at origination only. And actually, this is kind of important, right? Once you have long-term debt, and this is mistakes that a lot of models made, that means if you do one period debt, people are applying these limits every period. But this is kind of a problem, right? Because you only really get checked on your constraints when you borrow, right? So think about LTV. If prices fall and you have one period debt, that means people have to instantly delever, right? In reality, people deleverage slowly after prices fell in the bust. So this is something, I'm going to use long-term debt and make sure that these limits only apply at origination, which gives you that kind of slow deleveraging that you see. So the two things I'll apply are the loan to value limit that we talked about before. I just have some more I's and stuff on there because in principle, this is person by person. I'll also put theta LTV because now we're gonna have a couple parameters governing this stuff. And basically, the key property is it moves with house prices. So that when your house price goes up, you can actually borrow more, all right? Then on top of this, I'm gonna layer the payments income limit, which basically, so this is kind of your payment. R times M is your interest payment. That has to be less than equal to theta times your income. And then I have these other terms that account for the fact that there's some principal that goes into the payment, for example, as well as for this omega, is the fact that like in reality, you're supposed to count all your debt payments, including like your student loan payments and stuff like this. You have these offsets that you need. But the key property is that it moves a lot with interest rates. The elasticity is quite high, like we saw. All right, so when rates move around, the amount you can borrow, such as this limit, is going to move around a lot too. And what I'm going to assume is that there's some heterogeneity among borrowers in their income, and the overall limit is going to be the minimum of the two borrower by borrower. All right. So what does this look like in the data? So if you haven't seen this data before, it's kind of interesting. This is from Fannie Mae. And this is like kind of the post-bust. So this is when the constraints are being applied. I'll tell you more about what happens during the boom in a second. The left side are the LTV limits, okay? So this is like the histogram of LTVs. This is like a classic example of constraints, right? You just see these huge spikes at these round numbers where everybody is. So clearly, most borrowers are constrained by LTV. Now, not always at the same constraint. Why not? Because there's actually different kinks in the interest rate and there's different limits depending on if you want mortgage insurance and stuff like this, or depending on your other characteristics, but this is clearly a very binding constraint for people. Now the payments income limit is a bit weird because you don't see everybody in one massive spike, right? But clearly the distribution gets truncated at the formal limit, which is 45. So how many borrowers are constrained? I think there's actually a sizable minority who are constrained by this. It's not just the people in the very last bin. And what I think is happening is, remember, a lot of borrowers are targeting, like in that example, that exact price at which both the constraints are binding at the same time. But there's only $1 value of house that will deliver that, right? So what I think happens is borrowers kind of target that price, and then they don't want to end up with one that's bigger because that's kind of costly, but they're okay with ending up with one that's smaller. It's very hard to find the exact dollar value in a house. And what happens if you do that is then you're actually going to be on the left side where you're LTV constrained. You're going to max out the LTV and you're going to end up close to, but not quite in the final bin. So I've done some work since then to estimate how many people are actually payments income constrained. And you know, what you want to have in mind is a number like 25%. It's not everybody, but it's not nobody either. It's kind of a substantial minority that's bigger than this last bin. Any questions here? All right. Yeah.
You know, there was a time period where you could borrow to get the down payment. Right? That's not reflected in this data here.
It should be. It should be. Not borrowing from friends, but this is CLTV. So if you have a second mortgage, it should actually be showing up. That's one nice thing about this data as well. Okay, good. All right. So, you know, for support for this theory, if you actually do a cash out refi, you can't pick your house size. Then you're just stuck with the one you have. And you see here that the bunching, this is what would be predicted, is much bigger because a lot of people just get stuck at that constraint. You see a lot more bunching here, even though in principle, people who have had their house for a while already have kind of higher incomes and things like this. So I think that's pretty good evidence for this, but I have some more formal estimates that I'm happy to talk about another time. So what does this do to our kind of benchmark house price condition? So this was the optimality condition that I showed before. And we'll take a break just in a minute. So remember, if you know, this is the initial one I showed where there's no credit, or you're maybe unconstrained, or there's a constraint that's not LTV. In that case, you have this marginal rate of substitution, what I call the implied rent, plus the expected value of the SDF times the price times 1 minus the depreciation. Okay. Then what we talked about before is you can go to that kind of Yacoviello style model where we just add in the loan to value limit. Sorry, this is, I did different notation here. This rho equals 1 is not the rent. This is saying that you have 1 period debt. You refinance every period. I'll talk about this more in a second. And in this case, you have the second expression I showed you. Now, here's what happens when you layer in the combination of loan to value and payments income limits. That term mu theta becomes script C, okay? Where C is actually going to look kind of similar, but have one important new term in it. So what was going on? Remember that term, that mu theta, it was the collateral value. It was the marginal value from buying $1 of housing through the additional credit it allows you to get. So here we have something similar. We're going to have one more term, because when you buy $1 of housing, now $1 of housing relaxes your LTV limit by theta LTV. But only a fraction of borrowers at equilibrium have LTV as their binding constraint, right? So now you're gonna have to multiply this by FLTV, which is that fraction. So this is the total amount of credit in aggregate if you go across all borrowers that you know everybody buying on average $1 more of housing would get them, okay? And then you multiply that by mu. So you're gonna modulate this term by this FLTV term, and this is kind of the generalization of what we talked about before, right? So as you're moving around the limits, you're now going to be changing the fraction of borrowers who are constrained by LTV, and that's potentially going to be changing house prices through that channel, through this FLTV term, in a way that you wouldn't get just from an LTV alone, right? Then, in principle, I'm going to skip over this. There's something else you need to think about when there's long-term debt. I'm going to skip. So now here's the effect that is happening in the paper, which I call the constraint switching effect. So when interest rates fall, payments income limits loosen, okay? As a result, when these limits loosen, a bunch of borrowers are going to switch from being payments income constraints to being LTV constraints. That's going to increase the fraction constrained by LTV, FLTV, which is going to increase script C through this term, and increase house prices, which will then loosen LTV limits endogenously. By the way, here, when I say that by loosen endogenously, I don't mean theta LTV is going up. Theta LTV is the same, but even for the same theta LTV, when the house values are higher, you can borrow more against the same house. So now let's see this thing in action. I'm going to show you 3 different models that differ just by what credit limit we use. Now I'm going to compare the propagation of shocks. So the LTV will be just an LTV limit. Payments income economy will be just the payments income limit. And then the benchmark economy in red will be both of them applied borrower by borrower, the way I kind of explained. So let's see what happens. Now I'm going to shock this thing with a shock to basically inflation, right? So, real rates are kind of confusing because they actually change a lot of things. This is just going to be a shock to the inflation target. So real rates are basically not going to move, but the nominal rate will, okay? And that's going to be good for highlighting. I mean, it's actually been policy relevant recently, but it also is good for highlighting the difference between these models. So what do you see? So basically what you see is that in the payments income worlds, we get this big increase in debt because remember, lowering interest rates, nominal rates, expands that limit directly by a lot. In the LTV world, you get very little here. In fact, the only reason this is going up at all is because this is actually a fall in inflation, and this is measured as real debt. So actually, you get a little bit of less help than you expected from inflation eating away at your real balance. That's not very important. Here's what is important, okay? You'll notice, right, that like I said, I'm calibrating this model to match that only like 25% of borrowers in the red world are constrained by payments income, okay? But if you compare these, you'll notice that the debt response is actually closer to the world where everybody's payments income constrained than the world where everybody's LTV constrained. It's not 25% of the way there, it's more than halfway. And the reason is this endogenous amplification effect that we've been talking about. So you can see that unlike in either of these models, where the fraction of LTV is not really even an object, we see this thing increase. So as the payments income limit is loosening, more borrowers are becoming constrained by LTV. In this world only, that's pushing up the price to rent ratio. So neither of the other models actually have a very strong house price increase, but this world does, because in this world, when you relax the payments income limit, you actually expand the demand for housing and collateral. In the LTV world, it doesn't matter because there is no payments income limit, but also in the payments income world, if you don't have the LTV limit, you're borrowing, it's not even like a mortgage, it's like a personal line of credit tied to your income. So yes, you borrow a lot more, but there's nothing tying it to house prices actually. It's the combination of the two that gives you this effect. All right, so now let's just take 5 more minutes to wrap up this paper, then we'll take our break. So, so far I've been treating these limits as fixed and looking at what happens if you shock rates. But these limits changed a lot over the course of the housing boom, kind of like I mentioned. And I think this probably is related to automated underwriting. So this is the histogram of payments income limits post-bust. You can see clearly it's dropping off at this limit of 45, which is what Fannie and Freddie said after the bust. Now this is the same thing at the peak of the boom in 2006 Q1, okay? This data is Fannie Mae conforming vanilla loans. This is not anything about weird ninja loans or subprime loans. This is vanilla Fannie loans, normally underwritten. Okay, and you can see that basically there seems to be no constraint anywhere. The historical limit, by the way, is 36. So by the peak of the boom, you have about 60% of loans above the historical limit, and they're just smoothly increasing all the way up to 65%. 65%, by the way, of your pre-tax income being promised toward your recurring debt payments, at which point they top code the data. It could keep going, actually, I don't know. So this is really crazy. You see that this was a huge change, right? If you look at the cash out refi plots where we saw kind of even more bunching at the end, there's nothing during the peak of the boom. So this limit really seems like it was thrown out the window, okay? Yeah.
Do you happen to know if this is similar to 2014 in recent years, or if
it's going to be yeah. So it's a good question. So eventually they increased the main limit. So you can see here there's like a subset of borrowers who are allowed to go up to 50. They've kind of made that much broader. So you'd see kind of the same thing, but then the big drop would now occur more like at 50. And 50 is a pretty high number. So it has been loosened. Historically we're at 36. So it's almost 50% looser than like the pre-1990s standard. Yeah. So yeah, good question. Okay. So what I'm going to do now is run an experiment where I loosen either one of the two ratios or both. So I'll either loosen the payments income limit from the historical number 36 to just like a big number. You can see I could set this thing to infinity and it would match the data, but I'm going to set it to something close to like the 90th or 95th percentile. I can forget which. And then for the LTV, I'm going to increase this from 85% to 99%. There actually is not a lot of evidence that LTV was liberalized during this period. Oops, I'm pressing something. But this is something that was in a lot of people were talking about a lot. So I wanted to at least put this in to show what it does. Okay, and I'm going to compute some nonlinear transition paths. This is actually a great tool. I'm not going to talk about it too much, but actually, people often think that these big models need to linearize them. You don't. As long as you're happy with having it be a deterministic path, so the agents don't expect there to ever be any risk again, you can compute easily, very fast, the exact nonlinear transition paths to the new steady state. And this is really good for models that have some kind of nonlinearity or occasionally binding constraint. It's a great tool. Okay, yeah.
Are you going to talk at all about the impact of federal tax, property tax?
Not really. Maybe a little bit after the break. Yeah. Okay, so what do we see? So first, let's think about the LTV liberalization here. This is relaxing it to make it from a 15% down payment to a 1% down payment. That's the green line. You can see here that the price rent ratio is falling, right? This is that effect we were talking about before, right? Actually, when you have both constraints in the model, relaxing LTV can make prices go down, right? And what's going on under the hood is that now as you're relaxing LTV limits, the fraction constrained by LTV is falling because borrowers hit their payments income limits. That makes FLTV go down and reduces this marginal collateral demand. At the margin, you're not getting as much collateral benefit from your housing. That's causing the price to fall. In contrast, if you relax the payments income limit, that causes this FLTV term to go up. You get this big increase in prices that by itself is like a third of the rise in the boom. Okay, so what's kind of interesting about this as well, right? So remember, this is the constraint affecting like a quarter of borrowers, but relaxing this one has a huge effect. Relaxing the constraint affecting 75% of borrowers is a small effect. And that's all coming from the economics we talked about. Now you'll notice something else, that this also passes through to the debt thing here, right? So again, the payments income limit is being relaxed here. And that actually, because it's pushing up prices, it has a big effect on debt, even though only 25% of borrowers are constrained by this. Sorry, I should have said this before. Because by pushing prices up, it also lets the LTV constrained folks borrow more because they have more collateral. So that's why, even though more borrowers are constrained by this one, it actually has a smaller effect on debt because you don't get these knock-on effects through the house price going up. So that was why I kind of concluded that this payments income thing is really the main driver compared to the LTV. You can combine them, but I'm going to skip over that. So now, you know, there's other things going on as well. You also have interest rates falling, and you have some other mystery meat that is, you know, maybe people were just too optimistic. So I kind of feed this in until I'm explaining the entire boom in both price rent ratio and debt growth. Okay. And so what you can see here is that, you know, basically now, let me skip over some of this stuff and just show you my like macroprudential policy experiment. If I start by explaining the entire boom, and now I remove the payments income limit liberalization, remember by itself, relaxing the payments income limit drove about a third of the boom. But if I do everything and then pull that one piece out, I'm killing 60% of the boom almost, which is almost twice as big of an effect. So with these nonlinear effects, the order in which you add them or subtract them really matters, okay? And in this case, the reason it's happening is that think about like the effect of over-optimism, for example. Over-optimism, you have to be very optimistic about housing, but you know, during a boom, house prices are going way up, incomes are flat. So if you enforce a payments income limit, you might be super optimistic. You just cannot borrow a loan big enough to finance a super high house price, even if you think that's the right house price. And that actually makes these other effects like optimism much weaker. So this actually has its own direct effect, but also has very powerful indirect effects as well. Okay, so let's wrap up this part here. I'm happy to take questions, but then I know I went a bit long with the first part. So let me just say that adding these constraints matter. Changing payments income can have a big effect on house prices because of this interaction effect. And it seems to be really crucial to explaining what happened during the boom. Relaxing it by itself explains about a third of it, but removing it would kill about 60% of the boom due to this kind of interaction with expectations And as was asked before, these limits are pretty loose again. So I don't know exactly what's going to happen going forward, but it could well be a contributor to high house prices or potential instability going forward. Because remember, when these things are loose again, expectations have much more kind of freedom to run rampant. Okay, let's take a 5-minute break and then we'll do the second part. All right, folks, why don't we get started again? So I know it's, short break a lot, but I'll try to, I do have some more stuff I'd like to get to. So we'll see. Let's see how far we get. All right, so that kind of covers the topic of how these different mortgage limits work together, interact. So now let's talk a little bit about segmentation in housing markets. So the reason why, and this is going to focus on another paper of mine. So the reason why I did this paper is because I wrote this first paper. I was very excited about figuring out, oh no, it's not that limit that caused credit to affect house prices, this one, blah, blah, blah. And I realized unwittingly that I had stumbled into this much bigger debate about whether credit affects house prices at all, okay? Where there actually was like a larger debate about whether any credit limits at all played a role during the housing boom. So that ended up leading to this paper and kind of some of the ideas I'll share with you now, which I think actually, show up in a lot of places. So I think it will be useful to think about. All right. So this paper is called "Do Credit Conditions Move House Prices?" Right? Why did we think we needed to write a paper like this? Well, like I said, there's this broader debate in the literature about did credit matter at all, which is really fundamental for macroprudential policy. Right? A lot of macroprudential policies try to work by doing some intervention in credit markets that's supposed to affect house prices. If they don't affect house prices, good luck. Okay. So here's a couple of prominent and opposing examples of papers trying to explain the housing boom. They're both sort of very high-tech heterogeneous agent models with general equilibrium, Krusell-Smith stuff. Favelukas, they're both published in the JP. Favelukas, Ludvigsen, Van Nieuwerburg find that credit explains actually 60% of the movement in prices just from the relaxation of credit standards. Kaplan, Mittman, and Villante find that credit had virtually no effect on prices. So totally different results. And these are just two examples, but there's lots of different models out there trying to do this exercise and finding vastly different effects of credit on house prices. Some find it's very strong, some find it's very weak. Okay. Even more embarrassing for me personally. So my thesis committee was Gianluca Villante, Sidney Ludvigsen, and Stan Van Nieuwerburg. So like my committee couldn't even agree on this. This is ridiculous. So I decided I wanted to get to see what's going on here. So let's talk quickly about these models. May be useful for you to understand them. So the Favelukas et al. Paper is this large-scale heterogeneous agent life cycle model with idiosyncratic and aggregate shocks. And they find that this financial market liberalization, which is basically like a relaxation of LTV, is very important for the boom. Okay, and there's two separate contributions, which are kind of interesting. One of them I talked about. As you relax LTV, you increase that collateral value term. Another one they focus on, you can look at the paper, is that actually there's like a fall in risk premia due to improved risk sharing. So as you can tap more of your home's equity, that actually makes your consumption a little bit more stable. And that actually leads you to basically reduce your risk premium. And so whether this is going to hold up in the real world, I think depends a bit on how the contract is modeled. They're going to use one period debt. So they're going to assume that every period you kind of have like always have like a home equity line of credit on your house you can draw. And you can use this really well to smooth consumption. This is probably a bit overstated, but it is shown in kind of this Hurst and Stafford paper that your home equity is an important margin for smoothing consumption. So I think there's something there. Quantitatively, I don't know exactly how strong it is. This might be another area for future research. Okay, the other paper, Kaplan, Mittman, and Villante, they find that this kind of financial market liberalization, where they're going to relax both the loan to value and the payment income even, they have both of them, because Gianluca was my advisor, so I was always telling about this stuff, cannot explain the housing boom, right? So basically, what they find instead is that when credit relaxes, households want to buy more, but they just buy from their landlords, right? And this ends up increasing the home ownership rate, but not the price to rent ratio. And instead they find that shocks to the expectations of future rental growth explain the rise in the price rent ratio, okay? So this is a paper I wrote with Adam Gurin at BU. And so what we're going to do is try to reconcile these and say, okay, what the key differences between these and other models is the degree to which credit insensitive agents are there to absorb the extra demand driven by credit sensitive agents when you relax credit, okay? More practically, and this is going to depend on the degree of segmentation in housing markets. More practically, it's really going to come down to mostly whether the landlords in the model are willing to trade very elastically with the households. And if the degree of segmentation is basically how elastic is this willingness to trade by the landlords, okay? So that's what we're going to do. So we're going to look at the rental market. And there's two kind of main assumptions used in the literature, at least prior to this paper, but probably still. One is a perfectly segmented model where most commonly nobody rents. There's just everybody owns. That means the home ownership rate's fixed. Principle, I guess you have the same thing if you split the population. You stamped on your head if you're an owner or a renter, and there's different housing stocks for each of them. In this world, when you relax credit, it actually increases housing demand, which increases prices. Whereas in the perfectly frictionless world, you have these deep-pocketed landlords who don't use credit. And then when credit loosens, we have that effect we just talked about, okay? And I'll note that even though I'll focus mostly on landlords, this thing I said about divisible housing matters, because if you don't constrain the savers, if you have these savers and they have no frictions on their housing consumption and you have divisible housing, you can easily get them playing this similar dampening role on house prices. So I'll talk about that more in a minute. Okay, so the question that we're going to ask is fundamentally how sensitive are house prices to credit standards and interest rates? We're going to try to use a tractable framework based on the paper I just showed you. But it's going to have a new feature where we can sort of nest these polar cases as well as any amount of segmentation in between, which I'll define in a second. Then once you can do that, you have to know, okay, well, where should I set the model now that I have this entire spectrum of possibilities? And we're going to argue that there's a new moment we should be looking at, which is the response to the same identified credit supply shock. So for the same shock, you look at the relative elasticity of the price rent ratio compared to the elasticity of the home ownership rate. Okay, and this should be sufficient. And then we're going to calibrate the model to do this, and we're going to find our results. So what do we find? We find that actually, when you have an identified credit shock, the price rent ratio is responding at least 3 times more than the home ownership rate. Now that may not mean a ton to you quantitatively. That's why we have the model. When you plug it into the model, it implies that the relaxation of credit standards that we saw in the 2000s I just showed you explains, between 32 and 53% of the price rent ratio rise. So if you remember, this is pretty close to the numbers that I showed you before. That was what you call a full segmentation model where everybody owns. So actually, it turns out that the reality, according to our measure, is much closer to the perfectly segmented model where credit has a strong effect on house prices compared to this no segmentation model where it has almost no effects. So how do we find this? Let's go back first for some intuition. Okay, so what's the pattern that we actually see during the housing boom that's very anomalous? So, we begin, this is actually kind of like a Beveridge curve style plot. So what I've done is for the national price rent ratio, national home ownership rate, I plotted for every quarter the pair of these objects, right? And then I've connected them with lines. So prior to the boom are these gray dots. And you can see that the equilibrium basically lived in this lower left corner forever. And then during the boom period, it's kind of crazy to see, we get this incredibly anomalous increase up and to the right that we're, this region of this space that had never been entered before. Those are the blue dots. Then interestingly, the equilibria take almost the exact same path back down. The post bus is red before they end up settling kind of back where they started. So that's kind of the big event of the boom. It's this big simultaneous increase in home ownership and the price rent ratio. And then we traverse back down. So we go up and to the right and then later, down to the left. So I think that's kind of interesting, but it's also very helpful for thinking about supply and demand, what we're going for. So now what I'm going to do is think about changes in demand for owner-occupied housing and how these different equilibria could have occurred. So now we know that basically between 1998 and 2006, we had this big movement up and to the right in this graph. All right, now you can think of this like a shift in demand curves. So here I've drawn demand. The price is on the y-axis, quantity on the x-axis as usual. the reason why I'm doing the price rent ratio and the home ownership rate is because I want to point out this mechanism is separate from the elasticity of construction, right? So if you did just the quantity of housing on the x-axis, that would be affected a lot by construction. And construction could also affect a lot prices, because in areas with inelastic construction supply, prices will go up more after demand shocks than places with elastic supply. That's not the margin we're talking about here. What we're talking about here is the relative demand for owned versus rented housing compared to the relative price of owned versus rented housing. And this object should be pretty robust to construction. You know, if you build a lot, it doesn't say what the home ownership rate should do. And similarly, it actually doesn't say what the price rent ratio should do, because usually in these models, if you build a lot of housing, yes, it pushes the price down, but it also pushes the rents down. Okay, and actually there's no clear prediction for the ratio. So this is designed to be kind of the relative price, relative quantity, to be a bit more robust to concerns about construction. Okay, so now you can think, how do we get from this equilibrium to this one? Well, maybe one thing that happened is credit expanded and that shifted demand to the right. So now at any given relative price of owning versus renting, more households are willing to own rather than rent. And that's like a rightward shift in this graph. So now what's going on with supply? So first we have to think about what supply even means in this world. So this is the demand by households. Let's say households maybe who use credit. So if a household is buying from somebody, who are they buying from, right? So the models where we have perfect segmentation assume there's no one else to buy from. There's some amount of housing. The home ownership rate is fixed. It doesn't actually, you could construct housing, but the home ownership rate is fixed. Let's say this is 100%. So in this world, if you increase demand, but there's no one to buy from, it's like a perfectly inelastic supply. You'll see the price rent ratio go up a lot, which is what these models find. Now, of course, these models cannot explain why the home ownership rate went up because they assume it's fixed. But that does explain why these models find a big increase in the price rent ratio. Now, at the other extreme, you could assume there's a perfect rental market. So in this case, when the households go out to buy housing from somebody, there is somebody there who's not a household, a landlord, right? And these models typically assume these landlords, they're deep-pocketed, they're risk neutral, and they're willing to trade an unlimited amount of housing at a fixed reservation price, which is like the present value of rents, okay? So assuming the present value of rents doesn't change, which during the boom is kind of true-ish, assuming you don't change the landlord's reservation price, the new equilibrium with demand shifted is actually going to be at the same price rent ratio. You're just going to go out and buy a bunch of housing from the landlords. So demand does increase, but it's all satisfied by these landlords and the price doesn't move. And in fact, if you think about it in this world, the price rent ratio can never move unless you somehow either change the landlord's reservation price or you completely drive them out of the market and the home ownership rate goes to 100%. So in this world, how do you get from 1998 to 2006? You need to somehow shift this supply curve. And by the way, this is not construction supply. This is the landlord's price schedule, which in the paper we call 10-year supply, meaning housing tenure, not like professor tenure. And so what can you do? Well, you could, for example, shift this thing. Now, how do you shift the present value of rents? You could do one of two things. You could change the landlord's discount rate, that would work. Or you could change expectations of future rents, okay? And so in the Kaplan-Mittman-Violante paper, they use expectations about future rents. This is the only thing that's gonna work for them to get from here up to here. Otherwise, you're never gonna move the price. So that's kind of what's going on with these papers. So now where do we come in? Well, there's no law saying that these curves have to be perfectly elastic or inelastic. Like, yes, people do rent and the home ownership rate does move over time. So this world is clearly not correct. But the rental market may not be as frictionless as it seems either. So what if you had like an upward sloping supply, right? An imperfect rental market. So in that case, basically landlords are willing to sell you more housing as you buy more from them. But the more you buy, the higher the price you have to pay them, as with a classic supply function, supply curve. In this case, you could potentially explain the entire boom with a single shock that just moves up to this supply curve, right? But that's not really right either. There's no reason to think this specific thing must have happened. And in fact, for any slope between perfectly flat and perfectly vertical, you can come up with a combination of a movement along the slope and a shift in the supply that will get you from the start point to the end point. This is like a classic simultaneity problem. So what we need to do if we want to understand the role of credit, which is the movement along the supply curve, we need to understand the slope of this curve, okay, this supply curve. And that's what we're going to try to do in the paper. So basically, how do you measure the slope of a supply curve? We're going to do it the classic way. You find some instruments that should shock demand but not supply. Then you see where you go, and you take the y variable and divide it, the change in y divided by the change in x. Here, the change in y is the change in the price-rent ratio, and here the change in x is the change in home ownership. So that's what we're going to go out and try to measure in the data. Okay, we're going to take the same identified credit shock, the same demand instrument, and we're going to try to measure the change in price-rent ratio, the change in home ownership, and then divide the two. Okay, any questions here? All right. So we're going to use 3 approaches to do this, because we actually were able to find a bunch of off-the-shelf credit shocks. It's kind of nice because they're very different identification schemes. They operate using very different variation. And so we're going to use all 3 of them. Each one has kind of its own pros and cons, but when you put them together, I think it makes a more robust story. So the main one I'll talk about is this Lutskina and Strahan, which is about change in the national conforming loan limit. But we also do this DiMaggio and Kermani relaxation of anti-predatory lending laws, and a Mian and Sufi instrument about different exposure to private label securitization. So I'm going to skip over the data because I don't want to keep you guys too long. And so let's talk about this empirical approach. So we're going to use this shock, and it's based on the conforming loan limit. So the conforming loan limit is the maximum loan size that lets you be eligible for the GSE subsidy. So the GSEs, they charge you money, they charge you a G fee to insure loans, but it's not that G fee is too cheap, right? They're kind of undercharging you. And that makes GSE loans in some sense subsidized, right? Now, this CLL, conforming loan limit, changes mostly uniformly nationwide. So every part of the country will see this limit change. And everywhere it changes, it's kind of like a credit shock because it allows more loans to be subsidized when it increases. But the idea is that, what we're going to do is say, even though the limit is changing by the same amount everywhere, the effect of this, well, we're not going to, we're taking this from another paper. Lutzkin and Strahan said this, and we're going to copy them. This is going to have more bite in cities with more loans close to the conforming loan limit. So if you think about it, basically in San Francisco, housing is expensive. You have a lot of housing that's transacting at prices for which the conforming loan limit is like basically marginal. And so if you increase this thing, you bring in a lot of housing at the margin into getting this subsidy. It's a big shock to demand. In El Paso, Texas, the vast majority of housing is well below the conforming loan limit. There's a much smaller mass of housing at the margin. And so in El Paso, even though the conforming loan limit changes the same amount, you're going to have a smaller effect on demand. Okay, that's kind of the identifying variation. So then we're going to run this, and what we find basically is the blue is the price-rent ratio, the red is the effect on home ownership. Okay, the units are not that informative, but remember, we're not going for the absolute values. We care about the ratio. Okay, and so the price-to-rent ratio is actually peaking at like 16.5 compared to about 2.7 for the home ownership rate. So you can see that actually just visually, the price-rent ratio is moving a lot more than home ownership, which implies the slope is kind of steep of that curve I was telling you. Now, that's not really the best way to compute a ratio. So what we're going to do basically is instead formally compute this ratio and do a bunch of bootstrapping to get kind of confidence bounds for this. You can see at some point it kind of breaks down because we lose a significant response in the both of them are insignificant. So you take the ratio of two insignificant things and you kind of can't get anything good. But for the first 3 years, we get a pretty clear ratio. We're actually going to use the inverse ratio of change in home ownership over change in price, because you can see this thing is basically insignificant. So you get crazy looking things. So it's just simpler to plot the inverse where it's kind of well defined. And so this thing, usually when you get something that looks like this, you say, oh, this is garbage, everything's insignificant, but it's not because I did the inverse, right? So here, the fact that this thing is close to 0 and has an upper bound that's not very big is informative, because when you take the reciprocal, it means the point estimate's really big, and we can actually bound this thing to be at least like 2 or 3. Let me put it that way. So we do some more work to do this, but this is basically how we figure out the slope of that line, okay? By the way, we did a lot of work. So it turns out if you work with this data, that the census, the best way you can get home ownership rates going back far enough at the CBSA level is this census survey. This survey is super noisy. So we went back from scratch and made a new home ownership measure from deeds and address history data. We basically merged for most adults in the US, their address history, where they lived, and who owned the property. So we can look property by property at, is there anybody in common? And it's actually kind of a cool thing I'm hoping to do a lot more with. So if you have ideas, feel free to let me know. But anyway, once you use this measure, it's much less noisy because as opposed to being a very small sample, it's like most of the population of the US. And you can find home ownership basically is not reacting much at all. So actually the elasticity could be even, sorry, the slope could be even higher. This would be a slope, potentially very high slope, right? Here's what we now get for the inverse ratio here. And you can see we're able to bound it to be a very low number, which means the actual ratio is at least a very high number. Okay, I'm going to skip over the alternative approaches, but they actually find pretty similar slopes. All right, so now maybe this is the most important thing for a summer school. Before I get into the model, let me just go back over a little bit. What are the main things to consider before I get into the details? So in general, right, what you're going to need to get strong effects of house price with respect to credit are three things, right? You're going to need frictions. So I'm about to show you the model, but this is kind of like a little bit of preview just so you know the intuition for why things are there. You need frictions on trade with unconstrained owners of rental properties, right? So as we saw, if the landlords are these risk neutral, profit maximizing firms with perfectly elastic demand, they're going to absorb any change in demand. Price will not move. Similarly, if you have unconstrained savers, like we talked about, who are ready to come up and like buy these Las Vegas houses and stick them onto their Connecticut mansions, you're going to get the same thing, basically. They can have very elastic demand that will similarly pin down the price to be their kind of reservation price of housing. And if there's no frictions, they can also absorb the demand, right? And the third one is kind of one that, like I was saying before, goes a little bit under the radar, is about the latent demand for credit. So if you remember from our equations before, there was this mu term sticking around. That mu term determined how much house prices would respond to credit. And that is what I call the latent demand for credit. So changing credit limits only matters to the degree that households actually care about financing their house with credit rather than cash. And that's going to be something that quantitatively is very important to get right in the model. So the first two in some sense relate to the supply slope. If a household goes out to buy housing with a mortgage, who are they going to buy from? You know, can they buy from landlords? Can they buy from savers? In some sense now, there's actually two frictions we need to summarize. And we have one supply slope. So, you know, we actually can't pin them separately down. That would be a nice project for another paper. But what we're going to do, like I said, is we're just going to shut down the saver margin. We're going to assume there's none of these trades where people are packing up the Las Vegas house, bring them to Connecticut. We can relax this assumption and it doesn't completely overturn the results, but it's going to depend a bit on what you assume about the saver elasticity of demand. Now, item 3, like I said, is not about the slope. It's about how much demand is shifting following a change in credit standards. And this one is actually, I think, a little bit underappreciated. Now, in the end of the day, here's something important. It's kind of like all these are necessary conditions, right? If you relax any of them, it's not going to work, right? In some sense, any of these are kind of like a escape valve that can let off the pressure from demand, okay? So if you have a model like, because I've seen people say, oh, well, we have a model and we relax, let's say friction, we added friction 1 and we're still getting very small effects of credit on house prices. Well, that could be because you didn't put in friction 2 or because you don't have number 3, right? So in general, it's like the weakest friction is going to determine the effect, not the strongest one in these models, because people can always use one of these alternative kind of escape valves to get out. Or if households don't care that much about having credit anyway, you're always going to get small effects. So that's just something to be aware of. Okay, so what are we going to do in this model? Everything's going to be the same as the model I showed you before, except for one thing, which is now we're going to put in some heterogeneity within borrowers and landlords. So we're going to add landlords. I guess that's one change. And then we're going to assume that within borrowers and landlords, there's some heterogeneity. Why? Because if you think about it, if you just have two types, or you just have discrete types, and each of them, there's no heterogeneity within the type, each of them will set their own valuation for housing, okay? And then whoever values the housing more will buy all of it. So if you don't add any more heterogeneity, you're going to get a home ownership rate of 0% or 100%. So now we know we need some of it to match home ownership. But now here's the key. What I was telling you before with that supply and demand, that heterogeneity is going to map into these slopes of demand and supply, right? Because basically, the more, if landlords are all the same, they're all going to charge the same reservation rate, basically, the same reservation price, you know, that flat curve. Now, the more different you make the landlords, the more different you're going to make their reservation prices. So as you move from one landlord to the next, the more you're going to have to change the price on the supply schedule. So that heterogeneity in the landlord reservation price is going to map into the slope of supply. So this heterogeneity is going to be the key to matching that thing in the model, in the supply demand framework. So I'm going to skip over this. We do have construction, which I think is not going to be super important for what we're saying. I think I'll skip over this as well. And now let me tell you about what really does matter, which is this special form of heterogeneity. Oh, question?
Oh, sorry, I think you might be just about to answer it. I was going to ask what we should think of mapping onto landlord heterogeneity.
Yeah. Good question. Yes. So this is very important. So here's what I'm going to assume. I'm going to assume that each borrower I gets some extra benefit from ownership that they only get from owning. So basically, if they own, they get not only the rent. So this is kind of the imputed value of their housing services. Let's say that they own H housing. Each of it produces, you know, 1 unit of housing services, which you value at the imputed rent, right? But then I'm going to add on top of that you don't just get that benefit, you get 1 plus some omega shifter, right? And this omega thing is where the heterogeneity is going to lie. So that means that some households just get a lot of benefit from owning, even holding the amount of housing services fixed. Some get a little bit. The landlords too, when they rent a property, even though in some sense the renter is paying rent, just the rent, they're actually going to receive 1 plus omega times that rent. Okay, and here rent is the rent per square foot, let's say, and this is the amount of square feet. So what's the interpretation here? For the borrower, there's a lot of reasons why some households choose to rent and some choose to buy, even at the same price or same price to rent ratio. You know, where you are in your life cycle. Have you had time to save up the money for the down payment? What's your credit score like? Do you actually like owning, or do you not want to deal with replacing your boiler? Whatever, there's all kinds of different things. Some places where you might want to live, really the good housing stock is just for owning and not for renting. On the landlord side, it's a bit more interesting, potentially, or a bit trickier. The way I think about it is mostly about maybe the properties rather than the landlords themselves. So the implicit assumption, or sorry, what I have in mind, but this I think is open for research, by the way, but this is what I have in mind mentally, is if you think about the different properties rather than different landlords, well, some of these properties will be in like urban areas and big buildings that are full of different rented units. It's kind of efficient to monitor and maintain these units. You can have a superintendent that lives in the building. They're all the same. So if the sink breaks, it's the same as all the other sinks. Compared to you know, a sort of standalone house out in the countryside, might be one of a kind. It's more difficult to monitor. There's a lot more maintenance that's needed. So if the person is not taking care of it, it's going to be a big problem. You know, it's harder to fix, you know, et cetera. So that's kind of the idea. You take these properties, some of them are like very well suited to renting. The maintenance cost, for example, or the extra maintenance cost from making it a rental is not so high. Some of them are much worse for renting. They're really meant to be owned. So that's kind of what I have in mind. And so all I'm going to assume is that the owned housing is reallocated to the best suited agents of each type. So all the properties that have the highest, you know, benefits from ownership choose to own, and all the properties that are the most suited to renting are rented, and the rest are sold for ownership. Yeah.
Why do you need the two-sided heterogeneity? What does that get you additionally?
For this purpose, it doesn't get you a ton. So the heterogeneity on the borrower side is going to pin down the slope of demand. Heterogeneity on the landlord side will pin down the slope of supply. If you're just shocking demand, it actually doesn't matter too much what the slope was. If you have additional shocks that might also affect the landlord schedule, that's going to be moving up and down the borrower schedule, then it becomes important. Yeah, but I basically agree with you. Yeah. Okay, so now we're going to get back to the equations we've been looking at kind of all morning with a twist. So now instead of one equation, we're going to have two of these things. Okay, we're going to have one from the borrower side and one from the landlord side, which I'll call P demand and P supply, right? That's what's going to pop out of their optimality conditions. On the borrower side, we have the one we've been looking at, okay, which is basically that you get the SDF times the housing services. This is the rent you get per unit of housing. But then we're actually going to shift this by 1 plus omega bar, where omega bar is that heterogeneous benefit at the marginal agent, the last buyer who's buying. Okay? And then we're going to have the continuation value that looks basically the same as before. I didn't go over this last term, you can ignore it. It basically comes from the fact that if you have long-term debt, you don't transact every period, you have to actually remove some collateral value for the fact you're probably not going to use your house as collateral next period. But don't worry too much about that. This is the same equation I showed you before with one change. And by the way, this is the denominator from before, which if you remember, still has that same 1 minus script C term in there. The new thing is just this omega bar B. Then we have a second optimality condition from the landlord's perspective. And theirs is even simpler. It looks like the condition with no credit, where the price equal to expected value of the landlord SDF times the cash flow plus the continuation value of the housing that's not depreciated. But now that cash flow is going to actually get evaluated at the marginal landlord's omega L, or like the marginal property. And so at equilibrium, we have two expressions, but at equilibrium, they're going to have to be the same for the market to clear. That's how you can think about it. Now, how do these things line up? Well, let's say that the price demanded was too high compared to the price, the P demand is higher than P supply. Well, in that case, what that would mean is that the borrowers at the margin are willing to pay more than the landlords. So the borrowers would start buying from the landlords. That's going to push the fraction of borrowers who own up. But remember, the owners more suited to buy are the ones who own. So as this group of borrowers who own goes up, the marginal omega for the marginal buyer is going down because you're bringing in people who are less and less suited to ownership. Similarly, as you're buying housing from the landlords, more and more of their housing, they're selling you the properties that are the least suited to be rented. And so as you're buying from them, the properties are getting more and more suited to be rented, and the omega bar L is going up. So at equilibrium, that's how this model is going to clear, right? Basically, if the P's are out of alignment, then one group will buy from the other. As they do that, the shares of the different groups, the housing owned by the different groups is shifting, which is pushing around the omega bars until these things come back into alignment, okay? And as you can imagine, the more dispersed that the omegas are, the less that you have to move the quantity in order to have a big effect on the price, right? That's kind of the idea. All right, good. So I'm going to mostly skip over this. One thing I do want to tell you guys, because it is important for what I mentioned before, is there's always the underappreciated parameter of borrower patience, right? Which I think people often calibrate as a throwaway. It's really important. So here's how I calibrated it, if you ever run into this. I think it's kind of cute. So what I said is, look, about half of borrower, this is like basically about how much you borrow, you value financing with credit versus cash. And what I exploited here is the fact that at equilibrium, it's not exactly half, but it's maybe like 60-40. A big fraction of buyers, like 40%, I think, get mortgage insurance. And what the mortgage insurance does is lets them pay more to get more credit. So what I did was I calibrated beta B so that the borrower would be exactly indifferent between getting an 80% LTV loan or paying more on mortgage insurance to get a 95% LTV loan. Because this actually kind of pins down how much you'd be willing to pay for more credit. And it turns out if you do this, you get something very reasonable, around 10%. So my big takeaway is if you want to kind of do, why do I think 10% is reasonable? Well, because like mortgage rates used to be super high. Real interest rates, long-term interest rates used to be very high, and people were still pretty happy to borrow. So if you see models where the borrowers have a discount rate that's like 5%, I'm skeptical of that, okay? I prefer using something more like 10%. I think it's backed by the data and it's actually important for some of these results. But I think, again, this could be an area of future research. So what do we do basically? What I'm going to do is fit, remember, the key parameter is this heterogeneity of the landlord omegas, right? Which is going to pin down the slope of supply. And what I'm going to do is basically choose this thing so that if I run kind of my regression in the model, I can reproduce as closely as possible my findings from the data. These are my empirical findings for the price rent ratio and home ownership rate. And you can see that actually this is doing a pretty good job of fitting these, right? If you do the kind of alternative models, the like no segmentation, full segmentation, you can see unsurprisingly the no segmentation model would have a much smaller effect on prices, right? Because the landlords are absorbing most of the change in prices. The reason why it's not zero is because there are equilibrium effects on rents here. So that does get taken into account, but nothing else. Whereas in the full segmentation model, we would have kind of a slightly bigger, at least the beginning, rise in prices, which makes sense. Of course, the effects on home ownership would be reverse. With no segmentation, we'd have big effects on home ownership. With full segmentation, where the home ownership rate can't move, we'd have nothing. And we're falling kind of right in between. All right. We can add confidence intervals to this. But the point is that actually, when you look at this inverse ratio, if you kind of look at this one, the yellow line might look kind of okay. But if you represent it as a ratio, it looks totally crazy. So this is kind of like the benchmark. This is like our confidence interval, or these are the empirical confidence intervals as well. You can see the no segmentation model is just kind of flying off. We can reject it pretty easily. We actually can't reject the full segmentation model. Okay, so now I'm going to run the same boom bust experiments using my different models. Okay, this is going to be one that relaxes the LTV and the payments income at the same time. The red is my model where I've calibrated the slope of that supply curve. Yellow is a perfectly flat horizontal supply curve, no segmentation. Blue is perfectly inelastic vertical landlord supply. Okay, and the red shaded area is kind of my confidence interval that I kind of have taken away from my estimation. So now you can see that basically, what do we find? Credit is explaining like 32% of the peak price to rent increase, which is just, whereas, you know, much, much bigger than what we'd find under a no segmentation world, right? Just as important, right? This increase in prices, like we were talking about before, is also important just for the credit outcomes. Because a lot of borrowing, even though I'm relaxing the credit standards the same way in all these models, a lot of the work of the credit standards comes indirectly from raising prices. Because remember, when prices go up, anyone who's LTV constrained can borrow more. The benchmark in red is actually a lot closer to the full segmentation world, although of course, one thing we can get is we can get a non-trivial movement in the home ownership rate, whereas the full segmentation world would get nothing, right? Now, of course, this is just one shock, more things happened. So now you can actually add in the drop in mortgage rates. Mortgage rates fell by about 2 percentage points. You can see even here, because the landlords don't borrow in these models, which is not realistic, but that's how people usually do it. The no segmentation model would still say, whether it's the amount of credit or the price of credit, it has very little effect. Whereas now our benchmark model is explaining like 80% of the rise in the price rent ratio. It's quite close to the benchmark, but now we're explaining much more of the rise in home ownership. And actually, if you take our confidence interval into account, we might be explaining all of it. So this could be the whole story, basically. Finally, I'm going to do the same exercise as before, where I'm going to feed in shocks that give me the entire boom. You know, by the way, one thing that will always come up in these models, if you're wondering, is, which is another area for potential research, if you feed in changes in these models, the prices always jump instantly, right? Because everybody's forward looking. As soon as you put in new information, the price reacts. So all these plots, yes, it is true that this is too soon. And then you'll notice actually we don't get as big of a drop. Now the red line is the benchmark for the full boom bust experiment. We don't get this kind of deeper crash in the bust. That's because we don't have a financial crisis here. You know, people actually come out of the bust with credit limits. Mortgage rates are pretty low and credit limits are still kind of loose. So it kind of makes sense that they stabilize at a level above where they started. But in reality, we had this financial crisis that pushed them below for a while before they reverted. Okay, so I think both of these are potential areas for research. But I think this fit is, with those caveats, pretty good. And now you can see what happens in the gray line if we take the red line and then we just don't relax credit conditions. Okay, and you can see it's killing about half the boom in price rent ratios like before, but it's also massively decreasing the amount that people borrow, right? Both because the credit limits are not increasing, but also because house prices are going up much less. So you can see, even though we're not relaxing credit limits here, there is some more borrowing just because house prices are going up because of over-optimism and low rates, but it's massively dampened. Now, why is this important? Because if you did the same exercise with a model with no segmentation, you could still, again, you could fit the shock, so it explains the entire boom in both price rent and home ownership in the yellow line. But now if I remove the credit expansion, you have totally different implications. In this world, removing the credit limit expansion in the gray line doesn't really dampen the rise in prices at all. Instead, it just means that the home ownership rate would have been much lower along this counterfactual. And you can see this is important not only for prices, but also for leverage, right? Because in this world, even though we're not relaxing, the credit standards are the same, we have much, much more borrowing. Because in this world, the credit limits fail to stop the prices from rising. And high prices mean more borrowing, even holding your credit standards fixed. So I'm actually going to wrap up that part here. And then, well, I'm a bit over. So let me actually, if it's okay, take just 5 minutes to tell you guys a little bit about some research advice. So what do I think are some keys if you're looking for, if you're trying to do your dissertation? So the biggest thing that I think and these are things I wish I had known as a grad student. So one of the things is that a huge part of the value added of a paper is asking the right question, okay? Asking the right question is key to the research process. It's also very hard. I felt like you just start with the question and then you just answer it. Most of the job is answering it. But actually generating the question is really, if anything, harder. Good papers, in my opinion, ask questions about the world, not questions about a model. So take a model and say, what if I endogenize this? I think is not ideal. A better question is like, why is this happening? Okay. Now, another thing, and that's kind of model-based, but here's something which shows up in empirical work as well. There's a common question that I don't think is very good, which is people often focus a lot on statistical significance, which in some sense is a question of, is such and such exactly zero? I don't think that's a great question. Most things are not exactly zero. It's extremely unlikely that some number in the world will be exactly zero. But a better question is, basically, how strong is this effect? Does it matter economically? Okay. An ideal question for a job market paper is something that's so interesting and important that either outcome is a major contribution. If you find that something, like think about the paper I just showed you. I'm not saying this is an ideal paper, but if we found that markets were very close to fully segmented, that would have been publishable. If we found that they were very close to fully non-segmented, like that would have been publishable. Anything in between would have worked, right? What you don't want with a job market paper, because you're kind of on the clock, you have to finish by a certain date, is making a bet where the paper is interesting, but only if you find something surprising, because you may not, okay? The research process. So in general, if you're doing structural work, but also for empirical work, is I think you should have a reason for everything you include. One big thing is I really recommend starting as simple as possible and then building up as needed, right? This is good for two reasons. First of all, it gives you a lot of intuition for why you're getting your results. Because if you remember, oh, this is when I added in this step, that's when this thing started showing up. Then you know exactly what difference generated it. Whereas if you just have some huge thing that you've only run once, you have some effect, you have no idea which moving part generated it. This is extra important for a job market paper with a deadline, right? Because if you start with the simplest thing and then you keep building on it, you can just go with however far you've gotten. But if you start with something that's too complicated and you're taking things out, you may not have a working paper at the deadline, okay? So that's my 2 cents. Another thing I didn't realize early on is often we have something in mind about how we think the results should look. But I say, there's no point of doing research if we already knew the answer. So research, I don't know judo. I don't really know if this is true. But what I feel like is you're supposed to like use your opponent's momentum against them. You're supposed to go with what they're already doing, right? So what I say is like, if you're finding some results, like go with it instead of fighting it. If something shows up the way you don't expect, don't be like, oh, let me rerun this. Just think about why is this happening? This is interesting. Let me pull on this loose thread because actually that may end up being a more interesting result than what you initially thought would happen. And then another thing, this is something that Bob Merton always used to say, is apply more and more rigorous tests to your theory as it develops. So this kind of cuts in two ways. If you have a new idea, it's like a green shoot, like a little plant. You should be very gentle with it, right? Don't just think, oh, it doesn't match some fact of the data, I should just throw it away. It might still be okay. Be a little bit generous with it. But then as you develop your theory more, you want to start attacking it with kind of more and more serious tests to make sure it's really solid. So I would say at the beginning, give yourself some leeway, but as you sort of proceed toward publication or the job market, attack it with more and more serious tests. By the way, it's fine if your theory does not explain everything. It's just a theory, right? All papers have limits. You can break any regression by adding in enough things. You can break all models will fail to match something. So it's fine to be upfront about that. That's not a big problem. And I think the more upfront you are about that actually in your papers and your presentations, the better you'll do. It's completely, as long as your model is actually doing a good job or your empirical analysis where it matters. Okay, right, so research mindset, I think I actually said some of this stuff already. One big thing with grad students is complexity is actually not a good thing, it's costly. So adding more terms to a regression, adding more features to a model, it's actually costly in terms of complexity. You may be overfitting in various ways, you may be confusing the results. So make sure that you don't, it can seem like cool, like high tech, like you can flex your abilities a little bit to make things complicated, but you have to do it in a way that's really required and where you actually can show that that complexity is getting you something. Last thing, get feedback earlier than you think you should. I remember this very well. I think, oh, I need to get this thing kind of figured out before I talk to my advisor. No, your advisor is the one who helps you figure it out, okay? So if you come and it's already finished, they're just gonna say, good job. All right, so get feedback earlier than you think you should. Sorry for going a bit over and thanks a lot. I'm happy to chat more. I hope you guys will all say hi and tell me about your research. Thank you.